Okay, good morning or good afternoon, everyone. Welcome to IPnic eLearning web class. Today is the 8th of April in 2015. It's a Wednesday. We also call it as our e-learning day. And it's 1 o'clock in the afternoon. So we're now doing the second session for the day. The topic that we're going to cover is about IPv6 addressing and subnetting. Now, before we go on to the details of that, I'd like to first introduce myself very briefly. My name is Cheryl Hermoso. I work for IPNIC as a training officer. And as part of the training team, this is what we do. We conduct workshops either face-to-face or online, such as this. We attend different events in the Asia Pacific region to spread and talk about internet technologies. More specifically, we cover IP addressing, IP addresses, IPv4 and IPv6, internet resource management. We also do routing and BGP, network security, and DNS and DNSSEC. Now, for this particular session, it's under the IPv6 curriculum or IPv6 module. This class will run for 1 hour, and just a brief reminder that towards the end of the class, I will be asking you to fill in a survey. I hope you will take some time to do that because that helps the training team to gauge the viability and the effectiveness of these kinds of classes. These are provided for free, so we want to make sure that we are still giving enough for all the participants. Anyway, now let's go on with the coverage of this 1 hour session. It's about IPv6, and before coming into the class, I would encourage or I would expect you to have some brief understanding, basic understanding of IPv6. If you haven't done so, please watch a previous recording or maybe attend a session, which is first of the series. It's called IPv6 Overview. Now, if you've already done that, this is a continuation of that session, and we'll be mostly talking about IPv6 addresses and IPv6 address text representation. We will go through the IPv6 addressing structure, learn the different parts of your IPv6 address, the different types of v6 addresses as well, such as local, global address, and all that, as well as auto configuration. So we'll go through the details of that. Now, I don't think we will have time to cover up everything about subnetting, but I will discuss 1 or 2 examples and will leave you with some exercises that you can work on after this class. Right? Now, let's go ahead and discuss about IPv6 addresses. First of all, just a very brief introduction for those of you who haven't learned about IPv6 yet. As we all know by now, there is some issue, some problem, I would say, that we are now encountering with IPv4, and that is it is starting to run out. We are at the exhaustion phase. If you come to APNIC right now and request for your resources, you can only request a maximum of a /22 from the final /8 block. So that's very small considering if you're a new organization who wants to build up their network. So here comes IPv6. IPv6 is a newer protocol compared to IPv4. You can say that it's a newer version of IPv4, but they're not exactly compatible with each other, right? But with IPv6, when you look at the address space, it is so much bigger than IPv4. With IPv4, considering it has 32 bits in its IPv4 address, that is 2 raised to 32, which is around 4.3 billion addresses, right? With IPv6, this is now 128 bits long. So from 32 in IPv4, we now have 128 bits. That's 4 times as big than IPv4. But that's just the address. When you talk about the actual address space, it's not 4 times bigger than IPv4, but since we're talking about exponents, it is way, way bigger. We are talking about 2 raised to 128 possible addressable devices. So that's the number you can see on your screens. That's about 3.4 billion addresses. So that's a lot. So that's a very good um, um, way, I guess, to move into using IPv6, or at least introduce that into your networks right now. Now, to understand more about IPv6 addresses, we need to also understand IPv4, right? So I'm assuming that you're pretty much aware of that. We use it on a day-to-day basis. With IPv4, we said you're using 32 bits. But how do we represent an IPv4 address? How do you write your IPv4 address? Kind of said to speak louder. I'm already speaking very loud. We've already um, changed the volumes a few times from this morning. So if you can also check from your end to see how it is, that will be very good. Because I think I'm already at a maximum 4 hours microphones in this room. So I'm not sure if I can do more than that. Anyway, um, for IPv4 address, as I was saying, how do you write them down? You write an IPv4 address using dotted decimal representation, correct? You have a 32-bit address, you subdivide that into octets or groups of 8 bits, and then to separate that with a dot, and then each octet you represent that as a decimal. So that's why we call it as a dotted decimal representation. Now with IPv6, we're not going to use decimals anymore, okay? It's not dotted decimal. If you notice, right here at the end, we have an IPv6 address example. 2001 colon DC0 colon A910 colon colon. That's an IPv6 address. So if you look at it very closely, we're not using decimals. We're using hexadecimal digits. So the values are from 0 to F. Also, we are not using dots. Instead of dots, we are using colons. We are subdividing fields, okay? And each field, if you notice, has 4 hexadecimal digits. In IPv6 notation, by the way, 4 bits is also called a nibble. So 1 hex digit is a nibble. So that's what we normally call them. So since we have 128 bits, now if you represent that as hex, now you only have 32 hexadecimal digits. Okay, so if you look at each of these fields, A910, when you write them down in binary, you see that it consists of 16 binary digits. So each of the field will have 16 bits. Okay, so I hope you see the differences between V4 and V6. Right now, it looks overwhelming, but as you get used to IPv6 addresses, by seeing them, by writing them, by configuring your machines with IPv6, it becomes much easier. Now, we said that IPv6 has 32 hex digits, but when we write it down, we subdivide them into fields. And each field, as we noticed from the last slide, consists of 4 hexadecimal digits or 16 bits, right? So that means that when we write down an entire V6 address, it will have 8 fields. Okay, so it looks like this. That's a representation. And an actual example you can see in here. FE80 colon BCE3 colon all the way up to 683D. If you count them, that should be 8 fields. Each field has 16 bits or 4 hexadecimal digits. So it's kind of very long, considering that when with V4, it's very easy for us to remember, right? But in IPv6, if you have a complete V6 address like this, then it's very hard for us to remember any of them. Now, when you start writing down or deploying IPv6 networks, you will notice that when you get your IPv6 block, you will start from maybe the first /48 or the first /64 out of that /48. When you use the first few IP addresses, there will be heaps of zeros. There will be a lot of zeros. So this is an example of that. 2001, 0DB8, and then you have 3 fields that are all zeros, followed by more values there. So actually, when you're writing down a V6 address, you can write them down in simpler forms. So one example, as you can see in here, is when you have leading zeros and when you have group of zeros. Let's look at leading zeros first. If you look at this one, the third field has all zeros, fourth and fifth field all has zeros. Now this next one is 036E. So this field has a leading zero, meaning a zero on the leftmost part of the IPv6 field. Now when you write them down in simpler form, you can remove all the leading zeros. So 036E can now be 36E. All these zero fields here can be represented as single zeros in each field, as you can see on here. However, please note that these last two fields remain the same because they're not leading zeros. The zeros are not on the left side, they are on the right. So only zeros on the leftmost bit or the most significant bits of your field can be removed. So that's one. The next one is if you have zeros that are grouped together adjacently. So in this example, we have three zero fields. Each of them here are right next to each other, right? So what you can do is remove that altogether and replace it with a double colon. So 2001 colon db8 colon colon. So instead of writing down three fields of zeros, you represent them with a single colon. Now, why is this very important? Because if you notice, many of the IPv6 representations or symbols that have come to be are like the one in the ePnic logo, for example, are using double colons, right? So it has come to become a representation of IPv6 itself. Now, just please remember that in an IPv6 address, a double colon can only be used once in an IPv6 address. Because in this example, we know that there are 8 fields. We know that you have here a double colon somewhere. So we can easily assume, or we can easily compute that there are 3 fields that are replaced with a double colon. You cannot replace, let's say, if you have more sets of zeros there, you cannot replace that and have 2 zeros, right? I mean 2 colons. So basically, if I have another example, a similar one with this, I'm just going to write them on the chat. Like this one, okay, you have 3 fields that are zeros. You also have 2 fields that are zeros. How do you write them down? Okay, you can replace the first one, the first set, or you can replace the second set, right? Can you give me answers? What you cannot do is replace both with a double colon. Okay, Kana's answer is that's not exactly correct. The reason being is that you have there 2001 colon db8 colon 2001 colon db8 colon 36e colon. What's the last colon? We don't do last colons, right? There should be a field there. You cannot put nothing in a field. You can only replace a field with a double colon. So if you're not replacing it with a double colon, it has to have a 0, right? So the answer there is 2001 colon db8 colon 36e colon 0 colon 0. All right, so I hope that is clear with everyone. The reason for that as well is because if you replace both with double colons, it's ambiguous, it's vague. You don't know which one has the 2 zeros, which one has 3 zeros in the field. So it's kind of misleading. So again, only use a double colon once in an IPv6 address. All right, other things about IPv6 address representation that you can find in the RFC. One is, we've already discussed the use of double colons, but usually for consistency, the recommendation is to replace the rightmost set of adjacent zeros with a double colon. So for example, 2001 colon db8 colon 0 colon 2f colon 5. So basically the last set of adjacent zeros will be replaced rather than the first set. So in our example there, the recommendation is to use 000 colon 36E colon, something like this. So that is the ideal. However, it really depends on you, because in this case, you have more zeros on the first one, so most people would go with that. Again, this is just recommendations, but you can use it as your own will. Some would replace double colons, the part where you separate your subnet with your host bits. So again, it is up to you. Next one is if you are representing an IPv6 address on, say, a browser. If you're doing some troubleshooting, you're checking whether the domain is correct or not, or there's a problem with DNS and not the IP address, then this is what we usually do, right? We put in the IP address to go to a certain website. But with IPv6, can you actually just do that? Remember that in v4 terms, if you put something in a browser and you have a double colon, sorry, you have a colon somewhere, it means that what follows the colon is your port number. So you cannot do that in IPv6 just like that. In v6 address, you put a bracket, okay, to enclose your IPv6 address, and then colon followed by a port number. That's how you do it. But again, this is a cumbersome thing to do. It's not recommended. So most of the time, you must have a DNS. You put a DNS entry for that machine with an IPv6 address, and when you need to browse to it, you use the fully qualified domain name, right? More things, prefix representation. Usually, an IPv6 address is not complete without its prefix. So if you have 2001 DBA colon 12 colon, it's not really complete. You can say that it's just a single IP address. You can say that it's /32/48. So the thing is, for it to be able to complete, so you know which network or which subnet it actually belongs to, you must add a prefix. Okay, same as with IPv4 when you talk about CIDR. So 2001 DB8 colon 12 /40. That is what you assign for particular networks. All right. So just remember all of those things. Again, you can find them in the RFCs. One such thing is RFC 5952 and then RFC 3986, which contains information about this. Now that is out of the way, this is just a diagram of the entire IPv6 address, and when you write them down in binary, so we can see how big really is it, right? So you have a lot of ones and zeros if you write it now in binary. Next one is IPv6 addressing structure. Now that we know how to write down an IPv6 address, it's important for us to understand the different parts of the structure. And this also explains to us the sizes of IPv6 address that we can get from our ISPs, and then we can then delegate downstreams, or we can assign to our network. Now in an IPv6 address, you can subdivide them into two. You have the network prefix and the interface ID. Similar to IPv4, right? In IPv4, you have host bits, network bits. So it's something like that. Your network prefix is kind of like your network bits. Your interface ID can be loosely compared with your host bits. So the first 64 bits is your network prefix. The last 64 bits is your interface ID. Let's look at the network prefix first. So here you have 64, so your /64. This is where your network prefix should end. /64 is the smallest subnet that you should create. So that's based on best practices that we are doing now. Maybe it will change in the future, but now if you have a single, say, a small network, and that network only has 100 machines, okay, they all belong to the same subnet, then you assign a /64. If in the same network you probably change the topology, you only now have 5 or 10 machines in it, you still assign a /64. So basically that's the smallest unit that you assign to a single subnet. So you're only playing with this space. Okay? Now when you're doing subnetting, first of all, how much size of IPv6 address can you get? Typically, if you're a local internet registry, an LIR, or sometimes an ISP, a service provider, then typically you will get a /32 IPv6 block from the RIR. So if you come to APNIC now, you will get a /32 IPv6 space that you can delegate to your customers, right? That is an allocation. Now from there, you can now play from this value all the way to this value. So from /32 to /64, when you're doing your subnetting, you work on those values. Typically, if you're assigning to a big customer, okay, you assign a /48. If it's a very small customer, maybe a home user, you assign a /64. But you have to keep in mind that /64 again is only used for a single subnet. If your customer is expected to grow and maybe they want 2 or 5 or 10 subnets in the future, then you will have to assign more addresses to them. So you have to take all those things into consideration. All right, so that's a typical size, 32 and then 48, and then you work in nibbles. When I say nibbles again, it's factors of four bits, right? So you work on nibbles or factors 4 in between your 48 and your 64. That's your network prefix. The other part is your interface ID. Later on, I will show you how you can generate values for this interface ID, but that is the last 64 bits. So when you assign an address, you assign, let's say, 2001:db8/64 for the subnet, and then for each machine in that subnet, you assign the interface ID along with the network prefix, you get the IPv6 address. Okay? So that is the IPv6 addressing structure. Next one is the different addressing models in IPv6. If you are familiar with IPv4, this is actually very similar to IPv4. We have unicast, we have anycast, and multicast. One thing that is missing here is broadcast. In IPv4, we use broadcast, and we use it a lot. In IPv6, we are no longer using broadcast. So we're only tied with these 3 addressing models. The first one is unicast, which is when you send packets or messages from one interface going to another interface. One single interface to another single interface, you call that as a unicast address, right? With anycast, okay, one question from Ankit. Interface ID is host part in IPv4. Yes, loosely, as I've said earlier, you can think of it in that sense. Interface ID is like the host bits in your IPv4 address. Yes. Is that clear? If you have follow-up questions, please write them down in the chat. Meanwhile, let's discuss about anycast. So with unicast, it's pretty simple and straightforward. With anycast, similar to IPv4 as well, that's packet going from a single interface, but now your destination is consisting of multiple interfaces or a group of interfaces. In terms of anycast and multicast, they're kind of similar. Single interface as your source, destination, you have multiple interfaces. But what sets them apart from each other is that when you talk about anycast, only a single machine can receive this message, okay, among those that are in the group. When you talk about multicast, all of them get the same messages, okay? There's something good about having multicast. It's because your source machine or your host does not have to generate multiple packets going to different destinations. You generate a single packet or a single message, and this same message goes through all the destinations. It's like when I want to make a comparison or an analogy. When you talk about multicast, it's like when you're sending an email to a mailing list. So everyone who's a member of the mailing list gets the same email, but you only have to compose the email once. And everyone, when you send it, everyone still gets it. Right? So it's important to understand this because when we talk one of these, say, categories, I would say, or addressing models. They can be a unique IPv6 unicast address, an anycast address, or a multicast. And when we discuss them, you should have an idea of how this address is used, okay? Going from to a single interface only or going to multiple interfaces, okay? Any questions from the class? Again, if there are any questions, please feel free to write them down. I try to answer them as soon as I see them. Okay, so far we've looked at a few IPv6 addresses. Now, let's try to understand them in a bit more. In IPv4, we have different types of v4 addresses, right? Typically, we have a public address and a private address. A public address is something that is globally reachable, okay? You assign a public address to, let's say, servers, your routers, so that it can be reached by anyone on the internet, typically. Now, private addresses are, as its name implies, it's only available locally within your network, okay? So it's not globally routable. So that's with IPv4. In IPv6, we have some things similar that we will look more closely as we go on. But some of the network addresses or IPv6 addresses that you should be familiar with to begin with are loopback addresses, unspecified address, and those that are used in transition, v4 and v6. Loopback address in IPv4 is 127.0.0.1. In IPv6, the loopback address is this, ::1, okay? Why is it ::1? So it's all zeros, ::1. All the other fields are zeros. And if you apply the concept that we have discussed about shrinking your IPv6 address, you can remove all the adjacent zero fields and replace them with a double colon. You can also remove leading zeros. That's why it's very easy. It's very simple. ::1 is your loopback address. Again, an IPv6 address is not complete without its prefix. So you add a prefix there called /128, which implies that it's only a single interface. Okay, so that's your loopback address. Unspecified address is 0000, all fields are zeros. In v4, it's 0.0.0.0, right? So that's your unspecified address with v6. When do you see this? Typically when you haven't assigned any IPv6 address yet onto an interface, and once you've enabled it, this is the first address that it contains until it gets its IPv6 address, right? Next two ones are used for transition: IPv4 mapped IPv6 address and IPv4 compatible IPv6 address. As you notice, in this prefix notation, you're using 96. That is because you are allotting some portion of this address to put your IPv4 address. So from 128, 96, that means the difference is 32. That will now contain your IPv4 address. So when do we normally use this? If let's say you're doing some programming, or let's say, yeah, firmware or low level programming, and you want to assign, you want your code or your firmware to be usable both for v4 and v6. Sometimes you provide a variable that contains an IPv4 mapped or compatible address, and if it meets the IPv4, it will just pull the last 32 bits out of that variable, right? So that's the purpose of having IPv4 mapped or IPv4 compatible address. Other IPv6 address ranges that are worth noting, you already looked at the first two, but these ones, I'll look at them in more closely as we go on, but it's best that you have this in mind, at the back of your minds, so that when you see an IPv6 address, you have an idea what it's for. A global unicast address is 2000/3. Now, I would like to emphasize as you look at this, to notice the prefix. Here it's /3, meaning that this address is defined by the first 3 bits of the IPv6 address. In this case, it's 001. write them down because we write as hex. We need 4 bits. So you add the next 0 there. So that it starts with 2000. Alright? So the end of this range is 001, and then you replace this with a 1. So 0011, and all the rest are ones. So that means the last value for this range is 3FFFFFFF all the way up to the 32nd hex digit. Okay, that's your global unicast address. Your link local address starts with FE80/10. Again, it's defined by the first 10 bits. So that's 4, 4, 10 bits. So when you convert that into hex, that's FE80. Multicast address is FF00/8, and your unique local address is FC00/7. Okay, let's discuss these ones or each of them in detail. What are these IP addresses and what are they used for? As I've said earlier, we have already mentioned about the IPv4 public and private addresses. In IPv6, we have those things too. Okay, link local address can be considered as like a private address. Okay, with link local address, it's the first address that you get once you enable IPv6 on an interface. A link local address is mandatory. It's automatically assigned as soon as you enable IPv6. However, please note that a link local address is only, as its name implies, local. It's only available in the local link. So if you have a network with about 10 machines, you have enabled IPv6 on all of those machines, you did not assign a v6 address outright, but once you enable them, they should be able to communicate with each other. I should be able to send you packets, and I should be able to receive packets from the other 9 machines in the room. However, if there is, say, a router between this network and another network, subnet B, let's say I'm in subnet A, my packet will not go through the router because it's not within my local link anymore. I have to pass through a network device. So in this case, you won't get to see machines in the other subnet anymore. Link local address is assigned on a router interface. Any interface will have a link local address. A router interface obviously will have a link local address. If you have a host machine, a computer, or a mobile device that's IPv6 enabled, it can get a link local address. Okay, what I'm saying here is that if you have a router somewhere in between, okay, because you need some form of routing there, you will use a different type or category of IPv6 address. You don't use link local address to access a machine that is on another network. In this case, this is only for the local link. Okay, I hope that's clear with everybody. And the range for link local address is FE80::/10. So basically, once you enable IPv6 on your interface, have a look at it, do an ifconfig or ipconfig. You'll notice that there is already an IPv6 address there that starts with FE80. That is your link local address. Go to another machine, try to ping that IP address, then it should be accessible. Okay? The next one, which is, again, this one is already deprecated, but I just want to discuss that because it leads to the next one. So site local address, or SLA. So this is similar to the actual private address in IPv4. Okay, it is meant for that purpose, to be like the private address in v4. It starts with FEC0/10. Now, there's a reason this is already deprecated, and that's because with site local address, we're kind of defining the word site, and we are creating, or we will have an IP addressing only for that site. This IP address, since it's local address, can be repeated in other networks. But the problem is, how do you define the size or the range of your site? Okay, because because of that ambiguity, that fuzzy definition of the word site, okay, they decided to deprecate this and instead replace it with unique local address, or ULA. ULA is similar again to private address, or RFC 1918 in IPv4, but in this case, the IPv6 address that you will get is unique anywhere. Okay, it's unique anywhere and not just within one site. So there are places or websites that you can have a look to generate ULA prefixes for you. But if you look at the RFC, that's RFC 4193, it defines there that they can have a pseudo-random algorithm, which makes it improbable to generate two separate IPv6 addresses that will be exactly the same. Okay, so essentially you have a local network. Your IPv6 address is only usable within that local network, but anywhere on the internet, this IPv6 address will be unique. Okay, but this is not globally routable. It's only for local networks, similar to a private address. Unique local address uses FC00/7 for its IPv6 range. Now the next one is global unicast address. Now you will be excited because this one is similar to or considered the public address if you think of IPv4. So with this, this is globally routable. The range starts with 200/3. When you want to implement IPv6 and when you want your network to be accessible on the IPv6 internet, then you will need a range or block of IPv6 address space, which falls under this. So if you come to Epinik now and get your IPv6 allocation, it should be likely within this range. The range for Epinik region is 2400. So essentially what happened here is we have IANA, or the Internet Assigned Numbers Authority. They are the ones maintaining the entire IPv4 and IPv6 pool. With IPv6 from IANA, each of the RIRs received a /12. So you can see that here. Each of the RIRs, we have 5 RIRs in the world, received a /12. So if you come to Epinik and request for your resource, you will get your block, which is typically /32 or /48, from the /12 that is assigned for that region. So in our case, in Epinik region, that should be in the 2400 range. All right. So there are others. We have 624 address. If you're going to do transition sometime in the future from v4 to v6, then this is typically one of the address ranges that is used. This is used for one kind of IPv6 transition called 624. So with 624, they are assigned 2002/16. Okay, and you can try this. You can maybe peer with tunnels. There are some organizations that provides tunnels, and when you do that, notice that they will provide you with an address space that falls under this 2002/16. That again is for a tunneling transition called 624. Again, next one is examples and documentation prefix. Notice that in our previous examples, we normally use 2001 DB8. If you look at some examples in books, in perhaps some other journals or documentations, they will use this range. Why? We have a separate block that is assigned specifically for this purpose, for documentation or example purposes. And that is because we don't want to be playing around with real or routable IPv6 addresses only to mess up or announce prefixes that are not supposed to be announced, or use IPv6 addresses at and when someone else is already using it, right? So basically, this is in v4. We also have this. We have a range that is only used for documentation purposes. So please remember this and don't use these blocks to assign to your actual routers, okay? Maybe when you're testing, but not in production or not in your test bed. So in summary, those are the different IPv6 address space. If you notice, we have discussed most of them. This is reserved, so we didn't actually look into that. 2000/3 is our global unicast address. ULA, or unique local address, is FC00. FE80 is your link local address. FF00 is your multicast, and 2002/16 is 624. Okay, we didn't discuss some of the Anycast addresses here because we will be running out of time if we go in through all of that. But essentially, these are the most important, I would say, or the mostly used IPv6 ranges that you have to remember. So if you see FC00, you should know that it's already a unique local address. Or if you see FE80, you know that it's link local address. Things like that. Now, if you want to have a look of the entire range of IPv6 address space and how they are delegated or subdivided, please have a look at this link. It's in the IANA website, and it shows you all the entire IPv6 address space and how they are used. Any questions so far? So when we looked at those different types of IPv6 addresses, we're actually mostly looking at the network part, right? So mostly just the network bits. What about the other half of the IPv6 address? The other half, or the lowest, or the 64 bits, is what we call as the interface ID. So someone asked before, is this the host part in IPv4? Yes, you can think of it that way. So you can assign that in many different ways. Similar to IPv4, you can manually assign it. You can use a DHCP to assign it. But typically in IPv6, the more common ways to assign them, especially for end users, are one, auto-configuration. Okay, so we have a 64 bits range, and we will be using the MAC address of the machine to assign to that. Okay, we will fill in that 64 bits with a 48-bit MAC address. Another commonly used way to assign it is to auto-generate pseudo-random numbers. So most of the machines now, some of the operating systems, say for Windows, I think they're using pseudo-random numbers. For Mac OS X, they're also already using it. Linux mostly are using eui64. So what's the difference between them? I might have, yes, I have this slide. This is for eui64. So basically, we need 64 bits, right? We only have 48 bits because MAC addresses are only 48 bits. So what we do, we modify this. From MAC address, we subdivide that into two, replace or insert FFFE in between them, okay? So that's your eui64. Now, the reason it's called modified is because of this next thing. You look at the 7th bit. The 7th bit is typically most likely 0, okay? But whatever value it has there, you toggle that, okay? So if it's 0, it becomes 1, okay? And that is meant to say that this value or this IPv6 address is unique or not, okay? So in this case, since we toggle that to 1, this will now be 3.6, okay, as opposed to 3.4 before we made that changes. So your entire interface ID will be this 3.6 followed by your MAC address, followed by FFFE, and then followed by the last bits of your IPv6, of your MAC address. That's your IPv6 interface ID. Now, what is the downside? Let's just stick to this one for now. What is the downside to using eui64? You notice we are relying heavily on MAC address. In this machine, okay, I already know what will be the MAC address. In your machines, perhaps, it will also be the same. So even if I change networks, in each of those networks that I joined, again, you assign network prefix in a subnet. So I'll be using that network prefix. But for interface ID, I will be using this interface ID that is generated using modified eui64. So what does that tell us? If I'm in this network, or if I move to another network, maybe I moved overseas because I'm traveling and it's using IPv6 as well, my network prefixes will change, but my interface ID remains the same. So there might be some, for some people in the community, this is a security problem. So instead of that, they suggested to use pseudo-random numbers. So in this case, you don't rely on MAC address. Your machine, your operating systems will generate a random set of values that can then go to your interface ID. Okay, so that's what we mean by this second one. So in your computers, once you enable IPv6, as I've said, you can get a link local address. You notice it starts with FE80. Then look at the last 64 bits. Okay, if your machine is using EY64, then that will be based on your MAC address. If it's random number, then there's no pattern. You can't see any pattern. Okay, so just have a look at that. Once you're done with this, if you try to enable your V6, most of the operating systems already have support for that for a very long time now. So all you need to do is enable V6 and you should see a link local address. And notice the interface ID part. Now, as with all other host bits, you can still assign it manually if you want to do that. Typically for servers or for routers, or for any networking equipment, they would assign specific IPv6 addresses to them and not rely on the MAC address itself. Okay, so this is mainly used for hosts, because hosts you don't really care. It's for in its actual IP address as compared with servers or networking devices. All right, any questions for those two? All right, this one is zone ID. One thing that I probably haven't told you yet is that you have different types of IPv6 addresses, and you can use more than one IPv6 address in a single interface. Okay, again, you can use more than one IP address in one interface. For example, first IPv6 address that you get is link local address. On top of that, you can assign a unique local address. You can even assign a global address. So you can easily have 2, 3, or 4 IPv6 addresses for the same interface. So what happens if I want to access or want to maybe just send packets onto another interface? Where do I go? How do I know to route it properly so it gets to the correct range, right? So that's where zone IDs would come in. So in this case, for example, I have 2 hosts. I wanted to ping them. If I look at my machine, if I look at my interface configuration, you'll notice an IP address followed by some zone ID. If it's Windows, it's usually percentage and a random number. If it's Mac, it's usually EN plus a number, again a random number. So for you to effectively be able to send messages in between them, if it can't be done automatically by your machine, you have to specify or provide the value of the zone ID. Okay, so if you want to ping host B from host A, you ping host B's IPv6 address, which is FE80::something::3001, and then use your own zone IDs. Again, zone IDs are only local. It's defined by your operating systems. If you have %4 as your zone ID here, the other machine doesn't have an idea of that. You're basically just telling your machine which zone to use when sending these packets out. That is the purpose of a zone ID, and that is mainly because we have many different IPv6 addresses for the same Ethernet interface in your machine. Okay, I hope that's clear with everyone. Next one is auto configuration. One unique feature of IPv6 is stateless auto address configuration. Now there are 2 types in which you can address your machines, right? It can be either stateless or stateful. With stateless, that's normally when you are not concerned with the exact address. I've showed you some ways to do that in the interface I did earlier. If it's stateful mechanism, you want to assign a more defined IP address into that machine. So you most likely will use either manual IP address assignment or use a third-party machine or DHCP server to assign an IP address to that. Now, what is auto-configuration? This is more like how do you discover the machines on the network? There's a protocol there called NDP, or the Neighbor Discovery Protocol. In IPv4 terms, you think of this as when you are looking for um, logical addresses, physical addresses for logical addresses, right? When you're sending, say, IP address, so you use ARP. Here, it's kind of in that sense, but since in IPv6 we're not using broadcast anymore, so we use NDP protocol. We're not using things like ARP anymore. So how do you find out machines in an IPv6 network? Suppose we have this, a machine that has only been turned on. We want it to have an IPv6 address. So it will have a tentative IPv6 address, which is a link local address. That's what I told you about. You can have a link local address straight away. But even if it's like an address that will be assigned to that, this machine needs to check whether there is a duplicate anywhere else. So it will send out a message to everyone in the network checking if this address is unique or not. This is what we call as a duplicate address detection. Okay, so your machine will send a neighbor solicitation request, and then it will be sent to what we call as a solicited node multicast address. So not everyone will get this, okay, but only those that are listening into this multicast address. So that means if they're listening to this address, they probably have the same IP address, right? So that means it's a duplicate. So for us to assign an address to this interface, there should be no response. So if there is no response or no neighbor advertisement, then I can rest assured that this is unique. And so I can then assign an IP address. Okay, I can assign this link local IP address to my interface. Does that make sense? So that's it. That's a link local address. It's already been assigned. But what if I want this to have a global address or maybe just a unique local address? That is something that your router would announce. So your router, okay, will give a network prefix to your host. So now I want to have a global address. So I'll send a router request to the router. So I'll send a router solicitation request to the routers that are listening to this. So that's again going to a multicast address. And that address is ff02::2. Okay? If there's a router in the network, it will be listening to that address. And if he gets that message, he will reply back with a router advertisement. A router advertisement only contains the network prefix. So when I assign an address to myself, that will be using that prefix. And then the interface ID will be my interface ID. Okay, so you notice the interface ID part is the same both for my link local address and my global address. I only got the network prefix from the router. That's what you get from a router advertisement message. Okay, is that clear enough with everyone? Are there any questions? Right. If not, we're actually already kind of extending, but I'll just go very quickly with subnetting, and then I'll leave you with some things to do that you can verify with me later on. Now, what is subnetting? Subnetting is when you have a big prefix, an IP address prefix, and then you want to assign smaller blocks to different parts of your network, or maybe to assign to your customers. Now, suppose we have provider A, and provider A has been given a /32 block. So APNIC they requested an IPv6 block from APNIC, and it has been provided. Now, this provider will give /48 blocks to its customers. So the problem is, what are the blocks that I will give to these customers? In this example, we're only asked to find the first 4 blocks, but it will be more once you do your actual subnetting when you do your address plan. So one thing that should be clear when you're doing subnetting in IPv6, it's not different than IPv4. It's actually very similar. So if you're familiar with IPv4 subnetting, it is essentially the same. However, please note that here we are dealing with hexadecimal digits and not binary or not even dotted decimal. So either you switch from hex to binary, okay, or once you're familiar with it, it should be easy for you to work on subnetting just using hex digits, okay? So let's go through this example. First of all, it's always good to know like what's our actual block size. So in this case, we have a /32, and what we want to find out, we want to get /48 blocks, right? So from /32, that's just an extra field, okay? 16 fields, 16 bits in one field. That's your network prefix. Now, it's also good to know how many blocks you can get. So how many 48s are there in a 32? So this is how you compute for that. Again, similar with IPv4. So there's 2 raised to 16 /48 blocks in a /32. Now we only need the first 4, right? We only try to find the first 4. So we've already written it down as /48. So essentially, you know that your prefix is this one, okay? And you know that you're working 48, so you're working on this field. You're basically adding up or extending this. So you write this down in bits, so that's 16, and then you do your increments from there, okay? A word of advice, please know when you're using binary and when you're using hexadecimal digits. In a lot of cases, that's where most people get confused. In this case, the first 2 fields here are using hex. This ones in red are using bits, okay? So when you're in bits, it's easy. You just do your increments. So 0000, 0001, 0010, 0011. Easy, right? You just do your increments. However, this is not your actual answer. This is not your final answer. This is still in binary, so you have to convert it back into hex digits. So you write them down in hex. So the first one is 20010 db80000. Okay, so that's 0, 0, 0, 0. Okay, next one is 0, 0, 0, 1. Right? How about the next one? That's 0, 0, 0, 2. Okay, some people just write it at 0010, which is wrong because that is still binary. You have to write it down in its hexadecimal format. And then the last one is 003. So if you notice here, you're basically also just incrementing, but in hex. So that's 0, 1, 2, 3, all the way to F. Then you move to the next hex digit. All right? So that's how you do a simple subnetting in IPv6. Are there any questions? I noticed a few of you were writing down some things on the chat. Please go ahead. If you think that I'm already past that, it's okay. Just write them down and I will answer them as soon as I see it. So are there any questions with subnetting? Okay, if there are no questions, I have a few exercises here. We won't have time to go through this together. So please, on your spare time, maybe just after we close this, do this by yourselves. And then after that, if you want to verify, you can send me an email at training@ipnic.net and give me your answers and I'll let you know if it's correct or not. So first one is to get the first 4 /36 given a /32. And the next one is a bit more tricky. It's to find out your first 4 /35, okay, given a /32. Now when you deal with this, please write them down in binary because in that way it will be easier if you're just a beginner. Okay? Any questions? Any last questions from everyone? Now there are still many things to understand in IPv6. If you're thinking of implementing IPv6 in the near future, this is a good first few steps that you've already done. knowing IPv6 technical details by heart is a good thing. Then next ones would be to know how to assign IPv6 addresses onto your network, maybe do some address planning, and also understand how to transition from IPv4 to IPv6. So that's the next logical steps for you. Please attend those two sessions when they're available. So go to training.apnic.net/events for a list of our schedule. We also have a page on our IPv6 website that deals with everything IPv6. So go and have a look at those resources. Kind of said, yep, definitely. If you want to attend again, please do so. That will be good for us. If you want to visit or to review the videos that we already had, it's also a good idea to go to our YouTube channel. So that's youtube.com/apnic training. Okay, write that down. So we have previous recordings that are already uploaded them, so you can revisit and review them in your spare time. Again, next thing is to attend the other two more modules that is related to this. So have a look at that as well in the training website. Any other questions from the class? If not, I won't take too much of your time. Thank you very much, and thank you for joining me today. I hope to see you in the next session. The next one is at 3 o'clock in the afternoon. That's 1 hour from now, and the topic is OSPF. So if you have time, please join that as well. Again, thank you very much, everybody, and I hope you have a wonderful day. Bye-bye.